This is Dr. Jim Van Winkle. I took this class in corrosion from him at Portland State, and I really enjoyed it, and I thought he has a wealth of knowledge, like quite a few other professors at Portland State, so I'm hoping to work more with Portland State and important professors to come in and come and give us more meetings like this. So if you guys are interested in any topic, please let us know, and then we'll get somebody who can provide that for you. Without further ado, it's almost 6 o'clock.
Evening. I'm Jim. I'm out at Portland State University in the Mechanical Materials Engineering Department. I'm part of the Material Science and Engineering group out there. We just started in the last term our master's degree in Material Science and Engineering. And so at 2 or 3 points in the evening, I'm going to be giving you a commercial on why you should start to get a master's degree in Material Science and Engineering. Because the other thing that we have, and Andre and I were talking about it, and something that we'd actually like to work with people with, is continuing education programs. Again, people holding their PEs have to have so many continuing education credits. And PSU is trying to ramp up and get a lot more proactive with the continuing education program, bringing people in, and things like corrosion are the way to go. I'm a corrosion engineer. I'll actually run through my academic background here in a slide or two. The classes I teach out at PSU, I teach semiconductor manufacturing and diffusion, both of which are kind of wonky classes for the tech ends of things. But I also teach engineering material science, and I teach a corrosion class. The engineering material science, the whole idea here is we generate a lot of mechanical engineers who have a lot of really good structural data. They can do stress strain, they can put things together, but they really haven't looked at the materials. They'll say steel, and they really won't think much past that because they haven't been exposed to it. Or they'll make a logical leap and go, okay, stainless steel, without really going, you know, what's a 304, what's a 316? So that's the first chance I sort of get my hooks into them for material science, for how to actually look at materials and how to select materials. The other class I teach is a fairly traditional corrosion class, first half of which is corrosion science, which I will not even wave my hands over this evening. And the other half of it's corrosion engineering. And sort of the central theme I try to teach is the law of unintended consequences. You make a change in a material sense, and you wind up with something you didn't necessarily expect. You solve one problem, but you generate another one. And so that's kind of where I'm going to go today. First, my SAE street cred. This is my Lotus 7 clone. Running a 2-liter Z-Tech. Figure I got to throw in a card thing for SAE. Not pictured is my supercharged Miata, which is out hiding in the lot. I am a Colin Chapman disciple, for those of you who are in great cars. Simplify and add lightness. These are sort of, which means you start to look at things like carbon fiber for the fenders and the nose, and aluminum for the bonnet and for most of the body. Switching to aluminum leads into a number of sort of interesting problems, a couple of which we'll actually talk about today. And then where I came from. I got my BS in physics down at Oregon State University, at which point I discovered that a BS in physics qualifies you to wash dishes in America's finest restaurants. And so immediately jumped into a master's program in nuclear engineering, also down at OSU, where I first sort of got introduced to corrosion. I'd been a physical chemist before, and my goal was to study fusion physics, but there wasn't any real research money being funneled to OSU down there. So I wound up doing corrosion of zirconium alloys in reactor environments. So I got to really start to deal with really corrosion-resistant materials, which, again, we start to go back to those unintended consequences. We solve one problem, you know, we don't want this to oxidize too badly, and we develop another one. Zirconium creeps. And so all of a sudden we have these fuel rods which tend to want to stretch, tend to not to want to stay in shape down. And then I went to work for the Trojan nuclear power plant, Oregon's safest nuclear power plant. And after 4 years there, they cleverly decided to shut that one down for actually corrosion-based reasons. Okay, political reasons that were blamed on corrosion, but I can say corrosion-based reasons. Which launched me back into school. I got a master's degree in environmental engineering, studying hydrogeochemistry. water chemistry, things like that. And then my PhD is in material science and engineering, which is why I've been the program so much. Corrosion and electrochemistry. Corrosion-resistant alloys, actually developing electropolish for zirconium and titanium aluminides. The theory behind that, just briefly, is the finishing process for zircon for tialuminides was a pickle in a mixture of hydrofluoric and nitric acids. And the Oregon DEQ was starting to really shut down people who were putting a lot of fluorides out into the system. And so the fine folks at Huacheng were looking for something they could do to get a smooth surface finish without actually using fluorides. And so what I actually came up with was an electrochemical process to get sort of sub-micron smoothnesses without having to resort to fluorides. It was an electrochemical process, and then the DEQ got less interested, and they never put it into production, which is pretty much what happens to a lot of PhD research. Again, what I want to talk about is the law of unintended consequences. Finding a problem, identifying a problem, and then solving it. And finally, we created a problem which is harder to detect and harder to solve than the one that you thought you fixed in the first place. From a corrosion standpoint, what I want to talk about is start with general corrosion, which is, as all mechanical engineers start, we'll start with steel. And then steel rusts. That's a problem. Heat scratches in paint, that goes away. So the next step when you're talking about corrosive resistant materials are the autopassivating materials. And I'll spend a certain amount of time talking about the autopassivating materials, the aluminum, stainless steels, and titaniums of the world. And the types of corrosion that happen to them, which are often more difficult to detect and more difficult to deal with than the general corrosion you get on steel. Because engineers, they're design engineers, they put things together. Often they attach things together without actually talking to a corrosion engineer. We talk about galvanic corrosion, which turns out to be a huge problem. And this was actually where the idea of this talk came from. It was actually Andre's final paper in my corrosion class. It was actually about a mini Baja problem they had that literally halfway through my class he realized, oh, okay, this is what's happening. So we'll talk about that a little bit. And then, just because it's the enemy of corrosion engineers and automotive engineers everywhere, I'm going to talk a little bit about salt corrosion, why it's problematic. Who are my streamliner guys? Who are my salt floods guys? All right, cool. I already have my pulse review, so I expect questions. And again, if at any point if you have questions, go ahead and jump in. The simple one, steel corrosion. Iron and oxygen goes to Fe2O3, which doesn't cling to the surface. It's a different volume than iron, so it flakes off. It's non-protective. It's mechanically unsound. The thing about general corrosion is it's very predictable. If you know your environment, you can predict how much weight loss you're going to have in a particular piece of iron, which is why construction engineers don't care. They'll leave their girders outside. They know they're going to have a certain amount of rust go onto it while it's sitting out waiting to be welded up. It doesn't really matter. You design around it. So from a strength standpoint, it's pretty easy to design around. From how attractive things are going to be, obviously you can't design around it. And there have been a couple of solution methods. One classic was John DeLorean's idea that scratch paint leads to rust and iron leads to rust. Why don't we make the body out of stainless? As it turned out, in the mid-'80s, the only way to actually make this profitable was to sell large amounts of cocaine. And so that didn't work out so well. And also, they started to really trip over that first law of unintended circumstances, in that they found out stainless was a pain to work with from an automotive standpoint. You want to stamp out panels, and it doesn't go the way that your steels do for bodies. Welding it turned into a complete pain. You have all sorts of welding problems. And so you see very simple surfaces. The original designs had a lot more curvature to them, and they found that they were just not going to stamp those body styles out that way. It was, generally speaking, a failure, but it was a good try. I love this. Of course, I'm odd. I would actually drive a car with a galvanized steel body, so I'm the wrong person to ask. But 8,000 DeLoreans or so were built. They learned a lot. Several of them were painted, which I've never understood. But you put that much money into putting a stainless steel body on something. But the idea here is it's easy to take care of. If it scratches, you get your steel wool out and you buff it out. You don't have to worry about rust. They had all the required bumper sides, but it was hard enough. They really didn't expect too many dents and things as well. So this solution, if you will, was using an auto-passivating material, something that spontaneously forms an oxide on the surface. In stainless steels, it's the presence of chromium, which forms chrome oxide on the surface. In aluminum, it's aluminum oxide, Al2O3. Titanium, it's one of the titanium oxides, be it TiO or TiO2 or a suboxide mixture. The idea of the auto-passivating materials is the oxide form is thin, generally transparent. It's uniform, and it's protective, which is why you have aluminum cookware. You can trust it as long as you don't get too acidic or too basic. And so you have solved the problem of general corrosion. You now have a material, you can go out there and slap it on. Right now, Audi, I believe, is going to aluminum bodies in a very broad way on their luxury cars and the A8s. But again, painted aluminum. But still, aluminum's lighter, it's relatively easy to work with, people understand it. The difficulty in the auto-passivating materials is they are, by their nature, extremely reactive. Once they've reacted with oxygen in the air, you're fine, but if anything exposes the bare metal, they react again. This means that they're very difficult to cast. You don't cast aluminum in open atmosphere because it burns really pretty. Titanium even more so. There was a really interesting titanium ladle explosion down at, I think it was Timet last year. Basically, molten titanium hits water, you get a really large steam explosion, you get a hydrogen explosion as well. Apparently, this was in Albany, they could hear it in Corvallis. So these materials are a lot of fun to work with. They are also often a real pain to weld. If you're used to welding mild steel, it's all stick welding or using a torch, it's really straightforward. If you try to do that with titanium or try to do that with aluminum, you really don't get very far except for burning a hole in your material. So those things add to costs. They're hard to weld, they're harder to deal with. The other thing that happens that you don't necessarily expect, you've gone and you've solved this problem. It will no longer generally corrode, you will not have rust on the surface. The corrosion types that occur in auto-passivating materials are often subtle and really a pain to deal with. And the two that I want to talk about are pitting and stress corrosion cracking. A terrible picture of what happens in a pit. So I'll describe it first. Basically what happens on in a passive material is something in the environment breaks down that passive layer on the surface. Be it something like a chloride ion or mechanically scratching the surface. This exposes the pure metal underneath, and again, that pure metal is very reactive. And so it will immediately start reacting. What happens is you wind up with fairly rapid subsurface corrosion. The pits can be extremely small, but be through thickness in a relatively short period of time. In my previous life as a nuclear engineer, pitting was a very big deal because it was all pressure vessels. And you could design for a certain amount of scale or a certain amount of uniform loss, but you really couldn't handle pitting because you wind up with pinhole leaks, and a pinhole leak at a pressure differential of 1,000 psi turns into a really cool steam jet, turns into an extremely large hole. The other problems with pitting, again, it doesn't look like much. Often the pits are just little black specks on the surface. And unlike general sort of rust corrosion, you can't sandblast it off. You can't grind it off. You wind up with these very deep pits, often undercut pits as well. That, again, you wind up with fairly deep pit going often in a crystal direction with some sort of a cap on top, usually in a stainless steel it'd be a rust cap. In aluminum it's just a little aluminum oxide. But you wind up with very different chemical environments outside and inside the pit, and that's what drives the speed of the corrosion. And so in our class we go way too long on how to determine when pitting is going to occur and how fast it can go. Occasionally the pictures don't work so well when you blow them up. Stress corrosion cracking was the bane of my existence for quite some time. These passive oxides are ceramics, and as ceramics they are brittle. They can be quite hard, but they're also still very brittle. And so they can be fractured under stress conditions. And if those stress conditions are also in an aggressive environment, again, chlorides, acid rain, things like that, you could develop fairly aggressive corrosion in environments where the stress isn't enough to cause your material to fail. And the corrosion shouldn't be happening, but you wind up with these cracks that cause it to fail. The great difficulty is stress corrosion cracks are often extremely thin, very difficult to spot. The classic example, the example we had to deal with. When I was at Trojan, our steam generator tubes were made of Inconel 600, which was, it's a super alloy. We were going to be fine. Everyone told us this will handle all the temperatures you're going to put through it. And we wound up with leakers, and we actually had a couple of tubes get cut. And people really couldn't figure out why. One of the real problems with doing corrosion sort of engineering is A, you almost always get parts after they've failed. And so you get to look at the broken halves and try to see what happens. In boiler and pressure vessel areas, that means that all the evidence has probably been steam cut away. We had, again, about 1,000 psi pressure differential between the hot side and the cold side of the steam generators. And so any crack that made it all the way through would blow out any corrosion debris or anything like that. So we pulled tubes out, we cut them up, we took a look at them, and you wind up with cracks that look like this, that are actually intergranular. They'll run along the grain boundaries. Cracks like this will be a micron across, a couple of microns across. Not really a whole lot of obvious evidence on the surface. The other problem we had is we could take these apart and look at them and occasionally see cracks. So we wanted to be able to test the tubes in place. So 20-foot Inconel tubes that are bent in a U shape. The bore scopes didn't work. So then we went to eddy current testing, which seemed to be reasonable. If there are cracks there, you should have been able to pick it up by eddy current. But you learn that a crack which is open when there's a differential pressure of 1100 psi is a crack which is not open at all at a differential pressure of 0. And so we went back and forth with the testing people and the regulatory agencies, just trying to convince people that we could spot stress corrosion cracking when it was happening. Eventually, we had agreed to just plug any tubes which showed signs of leakage at extremely high pressure, and that was going to derate the plant to about 80%. But PGE, or our corporate masters at Enron, decided that inasmuch as we were fighting ballot measures every 2 years anyway, and they didn't want to derate the plant, and nuclear power is just bad. You don't want to get any of it on you, apparently. They decided to close the plant down. So essentially, Trojan was closed by stress corrosion cracking. The stresses that happen in stress corrosion cracking can come from a lot of different places. They can be thermal stresses, heating and cooling, or large plate thermal stresses where you actually have different temperatures on opposite sides. The big one that happens, residual stresses from, in our case, the tube bending process, or if there's a welding process going on. The sort of built-up residual stresses that happen around a weld, you can get really interesting stress corrosion cracks that run the entire length of the weld. Between that and sensitization in stainless steels, you can have literally corrosion failures where the whole weld, you can just pick it up and take it away and leave your 2 pieces of metal behind, which is disquieting for the people who wanted that to be 1 piece of metal, but from a corrosion engineering standpoint, it's really neat to look at. And then there are loads, all sorts of mechanical loads which can come on. And so, from a design standpoint, let's see, that's the picture. Again, this is a rivet hole with some surface cracks, again, very small. They can be fairly hard to spot, but they can get to through thickness fairly quickly. They happen with annoying regularity on aluminum. Anything with a lot of grain boundary segregation, a lot of alloy systems will also show this. Any place you attach components together, you will see stress corrosion cracking at rivets. You will see it at bolts. Occasionally under screws. It doesn't take a whole lot of load in a lot of cases. The other place that stress corrosion cracking and later galvanic corrosion happens a lot is any sharp edge. Any sharp edge you have, the atoms at the very end of that edge are in a fairly high energy state, and they will be corroded relatively easily. So something like a screw, which has been cold cut, you will get all sorts of corrosion both at the tooth and at the root of the screw itself. And then they pop off, which again doesn't make much of a screw. One thing Andre can tell you, I go about 700 miles an hour all the time, and if I had a whiteboard, I would have been drawing. So if you have questions or you need me to look, just yell. Politeness. Galvanic corrosion. This is another big deal that people should talk to corrosion engineers more often. They should, when they put a design together, they should just stop and say, hey, I put this together. And then after we're done slapping them, we discuss what's wrong and we fix things. Whenever two dissimilar metals are joined, and they're joined together in a way that they are electrically connected to each other, so just butted together, welded together, screw and sheet, whatever, with the presence of some electrolyte, something that will be able to carry electricity, the more active metal is attacked, often even if it would ordinarily be corrosion resistant. We operate on the galvanic series, where materials that overlap are generally safe to work together. Materials that are a great distance apart, there's a large driving force for corrosion to occur. The classic example being aluminum alloys and irons and steels. They do not overlap. People will still put aluminum rivets into steel sheet and then be somewhat amazed when the aluminum rots out very briefly. Aluminum is a real pain from a galvanic standpoint because really nothing we use overlaps with aluminum. You really can't mate aluminum with an awful lot of metals. The stainlesses will have two little bars here, either the active or the passive state. If it's got an oxide built up on the surface, it has one sort of galvanic reactivity. And if it doesn't have one, it has another, which means that they're also susceptible to galvanic corrosion due to wear on the surface. And so you actually see a lot of erosion corrosion and cavitation corrosion with stainless steels in aggressive environments because that passive film breaks down and it galvanically attacks itself. Some materials are actually galvanically attacked all by themselves. The classic example is brasses. Brass is a two-phase material, and the British found, while they were expanding the empire into, I believe at the time it was still Hindustan, that their brasses during monsoon season would develop these longitudinal cracks. They called it season cracking because it looked like seasoned wood. And what it was the zinc was selectively corroding out of the brass. And of course, if your brass starts to corrode that way, it's not really good to be shooting it. And so they wound up with a lot of ammunition failures. And that really sort of led to the first looking at what is the phase structure inside of a brass. Why does this happen?
Good question.
Sure.
How does zinc and mild steel get by galvanized?
Yeah, you do that intentionally because the zinc is preferentially corroded. And so you put the zinc on there to be corroded off. And the iron won't corrode at all until all the zinc is gone. And so the idea there is actually protect the iron by putting the zinc in there and letting it go. In marine environments, you do that all the time. You hang a zinc anode off your boat hull to keep your hull from rusting as well. Yes?
Have I not seen zinc on brass props too?
That's probably the same sort of thing where they're looking for that to actually corrode off first. It'll go relatively slowly because it's not terribly soluble as well, and so you won't actually get that breakup of the brass underneath, just the zinc will come off, is the theory behind it. And I'm guessing on that because that would be like galvanized steel.
Can you go back and talk a little bit more about the aluminum rivets in the steel panel and why they corrode quickly and what might the failure modes be?
Well, generally speaking, and in fact my example's a lot like it, because the aluminum, in that particular case, the aluminum is going to be the anode and the iron will be the cathode. So we're basically talking about electron transfer here. So the aluminum is actually going to oxidize rapidly. The electrons are going to be forced into it by the large expanse of iron there. And so what will happen is you wind up with this little powdery white, usually, corrosion product around the rivets. And again, they will go at any of the high stress areas first. And so around the neck of the rivet or where they're actually stuck through the sheet.
And what, how long do you think it takes to come to failure?
Depends on the environment. It's one of those, you start talking about saltwater corrosion, it's probably extremely rapid. Traditional sort of moist air, you don't have a whole lot of electrolyte on the outside to be carrying ions around, and so it'll probably be slower. So in the wet, it'll be faster in the wet, it'll be faster in acidic environments, it'll be faster in chlorine. The actual speed off the top of my head, I couldn't tell you.
Salt spray hours?
Sorry.
Okay. Thought it does.
It's an excellent question. I don't know.
So basically, then to prevent that, you provide a barrier to the
Provide a barrier between the two, something non-conductive. Polymer washer is one way to do it.
Right, just over the top, just to shield.
To make sure that it doesn't actually contact the electrolyte.
Yes.
Yeah. And again, this is two parts which have been taken apart. You get a lot of corrosion at the edges. Again, the corrosion will be most rapid where the two materials actually touch, and it will be more rapid anytime there's a sharp edge. The other thing you'll see in a galvanic series is you'll get undercutting as well. This is a bolt, cadmium steel bolt on top of magnesium, which again, magnesium is way at the top of the galvanic series. And you get undercutting corrosion. This will fall apart again, probably relatively rapidly, especially since magnesium oxide is relatively soluble. The example, sort of the what drove Andre to ask me to come here and why this went on. The PSU Mini Baja, relatively short cycle time, but they've got the Mini Baja. They're trying to save as much weight as possible, and so they wound up with an aluminum. It was an aluminum keyway and a steel hub. Aluminum hub. So basically, aluminum and steel stuck together. Then they drove it through the mud, and then they parked it without cleaning it off. And when they came back, there was this white powdery product on it. They were clearly losing aluminum. One of the big problems with this, especially in this particular circumstance, is that powder is aluminum oxide, Al2O3, which is extremely hard. And so now you've added something new to add wear to all the systems that are in the area. Because it's powdery, it will move around, it will grind things up. This is why when you have relatively short use objects. You take them, you clean them off. Either that or you don't trust them to students. And also you couldn't get them apart once you were done. Yeah. So that's the other thing. You start to get corrosion products inside the gaps between them, and it swells up, and you really can't take it apart anymore. You wind up throwing parts away or waiting for them to fail. But that was actually a really cool paper because it was very much a, classic galvanic corrosion. Would have been fine if it was dry. Probably would have been fine if you would have cleaned it off and let it dry, but you had a chunk of dirt on there holding moisture against it and giving it a fairly conductive sort of electrolyte over the surface. Just wanted to mention, because everybody talks about it, and well, you're automotive engineers. Best thing about Oregon is that we don't salt the roads, which means you can buy old British roadsters in Oregon. It's literally stunning. I have my friends come in from the Midwest, and people are driving around in MGAs, and they've never seen one because they last about a winter. Salt corrosion is, everything is wrong about it, is basically what it comes down to. It increases general corrosion rates. Regular steel that's exposed to salt water will corrode faster, measurably so. It's why the ASTM test for corrosion resistance is hot salt spray. Chlorides aggressively attack many of the oxides that are formed on auto pass fitting materials. And so in a chloride environment, you wind up with pits initiated. You can take aluminum, put it under water for roughly ever. Take aluminum, put it under seawater. Now you've got an environment where you may start to see pitting. It accelerates stress corrosion cracking by A, breaking down the passive layers, and B, being a much more conductive electrolyte. So you can push those electrons a lot faster, really push along in both SCC and galvanic corrosion. Push the electrons faster, push corrosion rates faster, lead to much faster failures. Which is why design in marine systems, coastal systems, one of my, it's a good example I give to the class because again, it's things people don't think about. A couple years back there was a walkway, reinforced concrete walkway at a NASCAR track, which gave way, collapsed. I don't remember if there were any people on it. They had taken their sand locally from, the beach and rebar, which there was no rebar left, and concrete by itself is a suboptimal bridge for a large number of people to go across. Again, it's one of those, civil engineers said, okay, we can do this. I don't mean to bash civils, but it's easy. Occasionally things get thrown at me, I'm used to it, don't worry about it. But if they would have taken a corrosion engineer and he would have gone, chloride. We do that a lot. But instead we come into the failure and people are going, why is the concrete full of brown stuff? And again, I just put this one up again because in a salt environment, you really accelerate the ionic conduction, the ability to move a current through the electrolyte, and so you wind up with much faster corrosion. We end my class talking about design for corrosion because I've now thrown all this corrosion engineering at the students just to give them basically a vocabulary and idea behind it, but then just kind of work through sort of design principles. Don't design anything where you have standing fluid in your system. If you have anything with an undercut lip and you leave water in there, you're going to cause yourself problems. Watch out for galvanic corrosion. I hit on them constantly for this. In places you don't expect it. You put in a hinge and you don't think about what the hinge is made of compared to the material it's attached to. You put two things together and you don't worry about them being painted because that's aluminum. And you don't have to worry about aluminum. And you wind up with stuff rotting out from underneath it. So if you're going to do things like that, you take things like you paint them, you coat them somehow. You put in non-conductive washers between materials like that. Avoiding narrow gaps in gaskets. Any place where you can have a small amount of fluid trapped in a very small space acts like an already initiated pit. And so often it is better to weld than to bolt. Gaskets which retain liquids can be a real problem if they allow water-based liquids to build up inside. Any of you have seen really cool under-gasket corrosion when you pull the head off. You had something wet in there and it was trapped in your gasket for long enough. And that, again, that's an unpleasant one because you're not getting it back in a lot of cases. And again, watch out for all your stress risers. More torque is often a solution to a problem that mechanical engineering students will use. Torque wrenches are for other people. But you start putting a whole lot of stress, especially on autopassivating materials, you can start to break down that passive layer and lead to the sort of stress corrosion cracking. Welding stresses. Jack DeVleeschen in the materials group is a welding genius, and all sorts of really interesting sort of, not only the chemistry that goes on in welding, but the thermal stresses and the mechanical stresses that come up from the solidification process and the joining process. Those are things you have to look at. When you're dealing with alloys that can pit or can be susceptible to fluid standing in narrow gaps, you have to make sure that you can trust your paint, that it's a bonding kind of paint. If you've ever been, and this is why on airplanes I love windows but not near the wing. Because A, you can just watch the cracks, and B, underneath the paint you can see filiform corrosion. You can see all these basically fingers coming away anytime there's been a break in the paint. And what's going on under there is the fluid underneath has gotten acidic enough that it's dissolving the aluminum. Because aluminum's amphoteric. It can't take acids and it can't take bases. I trust that the folks at Boeing have over-designed it plenty, but corrosion engineers, material scientists in general, should not sit near wings because you do nothing but think about corrosion and fatigue. I still fly and everything. And that is basically what I have for this evening. Like I said, I kind of shot through it. Question?
If you go back to the slide that had all the materials.
Yes.
So here's the question. What
Sure.
would happen if you had a painted bonded steel against aluminum with a stainless steel bolt? What would give up first?
Did you paint over the bolt? Or did you allow the bolt to be exposed to the environment?
Bolts exposed.
So the first thing to go will be the aluminum alloy because it's the highest in the galvanic series. So it will give up first, and then depending on where your stainless is, either the stainless is going to be relatively okay with the low alloy steel, or the low alloy steel will go next. But you will rot the rest of everything away to save the stainless steel bolt.
Okay, now, same question with different materials.
Sure.
Stainless bolt, zinc plated mild steel.
Okay. In that case, the first thing that's going to go is the zinc. And then you'll lose the mild steel, and then you'll lose the stainless steel. So they generally go in order. The thing about the galvanic series, this is a general series for seawater. The galvanic series is slightly different for different environments, different fluid environments. And so it can change if you know that your environment is acidic, or if it's not chlorides that are in there. Seawater is a good standard test, and more corrosion engineers care about it because it's also representative of what goes on in the human body. And there's a huge amount of research into implants and things like that. And so, again, the seawater curve, you see it everywhere. So they're similar, but they can be different depending on the material, or depending on the fluid that lands there. Yes?
On the common lead-acid battery, the posts and the connections often corrode. What's the process?
Okay. We've got, well, those are sulfates. And so it's probably ferric sulfate on the surface. There's probably enough iron in the contacts. You can't really make contacts out of lead. You have to make it out of something conductive. With as high a concentration of sulfuric acid as that is, copper won't work. don't think most steels will work. And so what you wind up with is just not, you don't want that sulfuric acid out, but that's almost certainly a sulfide of whatever the posts are made of. I can't imagine the lead will find its way out, because lead sulfate's also inside, but I can't imagine that coming out unless you get a major boil without a vent.
And if you let the battery discharge, you're more likely to get it.
You're more likely to have corrosion anytime you're running a current through something. So a completely flat battery, I would imagine, would be less likely to corrode in that way. I haven't done that test. I try not to run flat too often.
Right.
On the top of the scale here, we have magnesium. What kind of protection could you utilize on magnesium that would give it some reasonable life in a saltwater environment?
In a lot of the autopassivating materials, magnesium is sort of there. You can anodize it. You can intentionally build a relatively thick oxide layer on the surface so that oxide layer is not terribly easily attacked by the chloride ions. And so if you take something like magnesium and high temperature, medium oxygen environment, or you do an electrochemical anodization, we put a relatively thick oxide layer on it. Works great in aluminum, works reasonably well on titanium and stainless steel. I haven't done a lot of work with magnesium, but I would imagine you should be able to ceramic coat it some way.
Is there somebody local that does that?
That I don't know. That I couldn't even really guess.
Well,
Yeah.
We had a speaker a while ago on, I think he was doing the gas pipes, and they run a small amount of current.
Yeah.
Can you talk a little more about that?
Sure. In the same way that the galvanic series shows that materials can, the higher material is always corroded, but the lower material is always protected. And so if you've got zinc attached to mild steel, the steel won't rust at all until all the zinc's gone. You can actually replace the zinc, or the electrons it supplies, with an electric current. And so if you have a gas pipeline or an underground pipeline, especially if it runs concurrent with a power line, you can actually just drop power down to there and basically electrochemically protect the pipelines. Or you can use buried anodes. And if you have a pipeline that you can't get electrical power to, you bury zinc anodes every 30, 40 yards, which do the same thing. They give themselves up before the actual pipeline does. The place where that actually gets people into trouble is a pipeline that has a power line crossing it. The electric fields get really interesting around that area, and you can actually wind up with really odd localized corrosion right at sort of the edge of that field. And so they'll actually keep a real eye on that. And that's why a lot of municipal utilities would probably like to own both transmission and water. That monopolies your market.
have you ever heard, I had a guy tell me that if I hung a zinc anode on a carbon steel frame of a car, that would protect the carbon steel frame. And I couldn't figure out.
It works on a boat because you've got enough seawater and you've got enough current around it. The problem really with a carbon steel frame is only a spot of it's going to be wet, and that's where the corrosion is going to happen, and it's not going to be close enough to, this is usually where I lunge to the whiteboard, there's not an electrolyte sort of bridging those two for the zinc to be able to corrode first. And so unless the car is wet all the time, it's not really going to be able to protect anything other than really locally where it's hung. At the other end of the car, you just don't have a way to move the ions through the electrolyte. But there is one.
Another question, have you ever heard of people having success with powder-coated paint jobs and carbon steel frames?
Yeah, that's a reasonable way to go because you get a paint which is mechanically bonded and often chemically bonded to the surface and doesn't have any pinholes in it. And that's sort of the big deal with paints is you can't have any holes in them or else you wind up with basically pitting corrosion underneath any of those holes. Powder coat is a reasonable way to go for thinner surface. The only sort of downside to powder coat is I don't know if anyone, you can put zinc in your paint. And so if there is a scratch in the paint, the zinc or nearby will actually give itself up before the steel underneath, so you can touch it up before it starts to rust. I don't know of anybody who powder coats zinc into their paint. And so from a, do you guys?
I actually used to run a powder coating shop. They make, there's a company called HP Fuller that makes a zinc-rich epoxy primer.
Very cool.
And you put it on as an undercoat.
Okay.
And I don't know how well that works. I don't know much about corrosion, but
no, if you could get a powdered zinc near the surface, that's a lot of little tiny sacrificial anodes near your potential corrosion points. And so that would
I think the
work pretty well.
problem with it is that it's just suspended in another layer of powder, so only a certain amount of that is going to be on the metal.
Exactly. And so you'd have to do a relatively thin coat, which is probably why they did it as a primer, because you do need electrical contact between the zinc and the iron. It can't just be floating in the epoxy.
There's actually some other powders that have aluminum in them, I think, and other sort of they're conductive powder coating.
After World War II, there was a lot of zinc chromate primer around that they use on steel. Would that be?
That would probably run in the same, it's already oxidized, so I'm not positive. It probably wouldn't work as well as galvanizing it, but it would probably be better than leaving it bare. But that's not much of an answer. I don't know.
Do you think it'd be better than red oxide primer?
I think it probably would. Just because the presence of the zinc there, it's probably suboxide, so it can probably do some sacrificial oxidation. Yeah.
Have you done any work with some of the newer faster coatings, some of the zinc aluminum flake coatings for testing?
No, I haven't had a shot at any of that. I've mostly done refractory materials and sort of exotic metals, which is very cool, but nobody cares. And now I'm doing trying to do more practical research, and so that's one of the things I'm hoping to get hooked in more with the local industries and do sort of practical research kind of things. Check out my back. Yes.
Disc brakes in cars.
Yeah.
It's cast iron and I don't see any coating in it. You soak in water, you park it, you see rust in like half an hour. How do they survive their life?
Any rust that forms gets worn off, basically.
But you have like all the other edges and you have veins and all those things. I don't see any coating on them.
And there probably isn't. Again, as long as it's not on the surface you're trying to stop the car with, the rust anywhere else isn't really going to be too much of a problem because it's not going to be enough to affect the structural integrity, let's say, of the brake. Now, on something like a motorcycle where the brakes are not solid discs, they're really cut out, I'd worry about that a lot more because you could lose structural integrity a lot faster. But a disc brake on a car, those are hard to break. And so you could lose quite a bit of material and still keep quite a bit of mechanical strength.
Around town, around any town, there's a lot of fuel tanks around homes, very often. And a little bit of water collects on the bottom, and then they get rust. Now, is there something more going on than just the water and the steel and the rust?
Nope. Nope. It is just straightforward, rusting steel, puts a hole in it, fuel oil winds up everywhere, DEQ comes to your house with a backhoe.
10 grand, just like
Yeah, leaking underground storage tanks. At least they gave it a good acronym. But yeah, that's in Oregon. The lust problem is DEQ is big on it. I've had a couple friends selling houses with underground oil tanks that they just decommissioned it. They just, made them as empty as they were going to, filled them with concrete, said they never leaked, and walked briskly away from the house. Just because it's expensive to test, and if it's wrong, like I said, 10 grand, easy, and yeah, they show up with the backhoe.
I was wondering if any stray electric currents might have
That
any
could
effect
certainly
there.
speed things up, but it's not necessary. Because I doubt they coat those tanks very aggressively when they're put in, especially older ones. Because it's just oil. Oil's not, it's a rust inhibitor. We don't have to worry about this at all. We'll paint the outside. And then water gets in the tank because no one ever plans on water getting in the oil tank.
If
you talk a little bit about anodizing of aluminum and how it helps and why it doesn't last long in applications where there's deformation.
Well, the reason it doesn't, okay, the idea behind anodizing is to put a relatively thick layer of aluminum oxide on the surface, because aluminum oxide is really hard, is by itself relatively corrosion resistant. But as soon as you try to deform that anodized piece, that's just going to break. It's a ceramic, it's just like taking a piece of alumina and trying to give it a 15-degree bend. It'll break underneath that load, and you wind up with an anodized surface that's basically fractured. Unless you're asking something which has been deformed and then taken to be anodized? Okay, no. Okay. Basically, the reason is the surface is relatively brittle. It's aluminum oxide, which ductility is about nil. So, yeah, it's entirely that.
And then focus, high stress.
Oh, especially, yeah. And it's relatively strong, but again, it's brittle. As soon as there's a crack in it, that crack will propagate. So it's good in sort of wear conditions, but not necessarily in impact mode.
They've used salt and roads for melting ice for years, and then they decided there had to be something cheaper, so they started coming out with other chemicals. And they would stay on the road, and they did a good job, and everybody was happy because they were saving money, and then all of a sudden, all these trucks started falling apart, especially at the electrical connections that were kind of in areas where salt didn't get to. What's going on?
I'm guessing they use a different chloride. Instead of sodium chloride, probably use something. It's mag chloride? Yeah, lovely. And magnesium ions are going to give you an extra oxidizer in there as well as the chlorides. And so now you've got an aggressive ion and you've got an oxidation source. And so that is a recipe for starting a pit or starting corrosion or accelerating corrosion. Yeah, mag would make sense because it's cheap. You can eat it. Well, they have trouble with throwing toxic things on the road for some reason.
I was going to ask about, can you talk a little more about elevated temperatures and corrosion and how it...
In which sense?
Like the jet turbine blades.
Okay. You wind up with relatively small numbers of alloys you can use in temperatures that high. Because they have to be able to hold strength, and they can oxidize a little bit, but they really can't oxidize thoroughly. And that's why the nickel-based superalloys, almost all the high-temperature, high-speed alloys are nickel-based superalloys, often with quite a bit of chromium. And the reason there is nickel resists high-temperature oxidation relatively well. The nickel oxide that forms on the surface is stable, stops additional oxidation, and they're high strength, especially high strength at temperature. That's why everybody thought Inconel was going to be fine. It's nickel-based alloy, it's got plenty, it will be fine. In addition to the stress corrosion cracking, we also had a transporting iron scale onto this, and then a piece of iron oxide on a piece of nickel-based superalloy, which turned out to be an intriguing problem for a lot of different reasons that we could design around that. So that's more of just sort of a selecting materials that can handle the temperature. I can do a 2-hour lecture on high temperature oxidation, I just don't know if I can summarize it. The activation energy of oxidation is sort of the key, and nickels is relatively high, so it doesn't oxidize very rapidly the way other materials do, and it holds its strength. And you can put it together in single crystals, which is the other cool thing about turbine blades, is you can zone refine them until you have single crystal turbine blades. Now you don't have grain boundaries that can come apart on you under the high stress, or grain boundaries that can be attacked by the oxygen or by just the high temperatures involved. Nice single crystals, they all expand and contract uniformly. You don't wind up with the little chemical segregation that happens at grain boundaries as well, where you wind up with all your impurities at the grain boundaries. So that's where all your corrosion starts. Single crystal superalloy, you can see that. Something like 718 or Aspen C.
What about so I think some of the equipment trucks uses high strength steel, 100 indicated is, are those more, because I think they use more higher carbon in there?
Yeah.
Are those more susceptible to?
Not particularly. The carbon content in steels doesn't really affect the corrosion resistance. Adding things like nickel and chromium will have a much larger impact on corrosion resistance.
Will it make it corrode faster because of the?
No, unless you wind up with, I can see in some cast irons you wind up with the little graphite nodules, but I doubt that high strength steel, I don't know. I just can't picture, say, lower bainite having a higher corrosion rate than say, perlite.
You talked a little bit about electrical current accelerating corrosion, but then you also gave an example of the electrical current.
You just basically have to be pointing your electrons the right direction. So it's a matter of selecting your potential. Positive potential protecting it, negative potential causing it to corrode faster. And so it's which terminal of the battery you connect it to, basically.
This is an off the wall question.
Sure.
What, do you have any idea what the odds might be of nuclear power plant here restarting something?
Of Trojan itself, or just in Oregon?
No, really.
Trojan is nil. The reactor vessel's out into Hanford. They'd have to build it from scratch.
Start over.
Yeah. The only thing they have the site, and they have the containment building, and they could probably still use the control tower, not the control, the cooling tower. 499 feet tall. Anybody know why?
No.
Any pilots?
500 is the limit?
500 feet, you have to paint it yellow and orange, or white and orange.